Today I will tell you about basic computations in geometric optics. The video consists of two parts. The first part will discuss ray diagrams, which is a simple technique that allows you to find properties of basic optical devices. In this part of the video, we will complete a 1-minute exercise in which we will practice how to draw a simple ray diagram. So prepare a piece of paper, and when I ask you, we will pause to write down your prediction and then find the answer using the ray diagram technique. Geometric optics is a part of optics that investigates propagation of electromagnetic waves whose wavelength is much smaller than the typical distance that the wave travels. In other words, geometric optics applies to any wave when the wavelength is small enough. Under this important condition, the direction in which the wave travels through various media can be predicted using a so-called ray approximation. We will apply the ray approximation to describe the electromagnetic waves, such as visible light. But in fact, this approximation is much more fundamental. It is a consequence of a general mathematical equation predicting how waves spread through the materials. It may be applicable to many kinds of waves, including waves on the surface of water, sound, tectonic, and gravitational waves, and even quantum wave functions describing properties of atoms and subatomic particles. In our class, we discussed two main tools of geometric optics. One is called a ray diagram, which relies on the ray approximation. The second tool is a so-called mirror equation or a thin lens equation, which in reality is the same equation applied either to mirrors or thin lenses. Whenever solving optics problems in your assignments, you must always apply both methods to solve every problem. First, you must sketch a ray diagram indicating the directions of the rays of the wave and use the sketch to predict positions of the object, image, and answer any other questions. Next, you should find the same positions using the mirror equation. Both methods must produce the same results. By comparing these results, you verify that you did not make a mistake. In particular, the distance found from the mirror equation can be positive or negative, depending on whether the image appears in front of the mirror or behind it. We will discuss the rules for assigning the signs to the distances later in the video. By comparing the sign of the distance that you found from the mirror equation with the position of the image that you see in your drawing, you can confirm easily that your calculation was right. Let us now discuss the first method based on ray diagrams. To start, let's recall that a ray is an imaginary line describing propagation of the wave. The ray indicates the direction of the wave at every point through which the wave travels. Rays are merely a trick to visualize the flow of the wave. They don't exist in reality, and the wave of a very complex shape would require multiple rays to describe its properties. But if a wave is simple enough, it suffices to use just a few rays to get an idea of where the wave goes. Say, for a plane wave emitted by a long light bulb or a laser, you only need to draw one ray, called the principal ray. The other rays will be parallel to the principal ray at every point and need not be drawn. On the other hand, a wave emitted by a single point-like source, such as a light bulb, propagates radially from the source in all directions. Its wavefront is a spherical surface of increasing radius. You will need many radially diverging waves to specify propagation of such a spherical diverging wave. Nonetheless, in simplest optical systems, you need only a few principal rays to predict where the image will form. We will now practice with selection of these principal rays and reconstruction of images. Now let us take a piece of paper and spend a few minutes on the following exercise. Imagine you look down into water on an object that is inside water, for example, a fish that swims at a certain depth. Suppose you look at the point P at the top of the fish, let's say the upper fin of the fish. Where will this fin appear compared to the actual position of the fish? Will it appear at a greater depth than it really is, at the same depth, or at a smaller depth than it really is? Write down your prediction. Okay, now let us find the answer by using a ray diagram. What I would like you to do now is to pause the movie at this slide for a few minutes, draw the eye of the observer, water surface, and point P on the top of the fish. Next, I would like you to sketch a light wave that goes from P to the water surface. In other words, the light will scatter on the top of the fish. Some of this light will be reflected back to the observer. How will the shape of the reflected wave look like? Will it be a plane wave or a diverging wave? If you don't remember what the plane wave and diverging wave is, see a few previous slides. Well, in this case, the wave is diverging because it is radiated from one point on the top of the fish. This point looks like a point-like source, so therefore, the wave that is produced by a point-like source is diverging. Next, I would like you to indicate the direction of the light wave in water and in the eye using the rays, which are imaginary lines indicating the direction of the wave at each point. So draw two or three rays starting from point P, going to the surface and then to the eye, paying attention to the refraction of the wave at the boundary of the surface. Find a point where the rays that reach the eye would intersect if there were no refraction. This point is the image of P. Let us now do it together. First, we will draw several rays indicating directions of the wave. These rays will bend at the surface. In the air, the rays will travel at new refraction angles to the normal line drawn to the surface of water. The refraction and incidence angles for each ray are related by Snell's law. Most of these rays, indicated by blue lines, will miss the eye. The observer will not see them. Only some rays, shown in red, will reach the eye of the observer. Roughly speaking, these rays should be close enough and within a solid angle seen by the eye at that moment. Within a small fraction of a second, the brain will subconsciously process the electric signal sent by the eye and reconstruct the apparent position of P, called the image of P. The algorithm in the brain works in such a way that the apparent position of P is at the point from which all visible rays seem to emanate, assuming that all rays are straight. To find the image of P, we trace the visible rays back along the straight lines to the point where they would intersect. As you can see, the image of P in this case is above and to the right of the actual position of P. So to the observer above water, the fish appears at a smaller depth and to the right from where it actually is. Okay, so this was the simplest diagram that you could create. Obviously, the diagrams for mirrors and thin lenses will be somewhat more complicated. For the next step, I would like you to watch a few lectures at the website called hippocampus.org showing how to draw ray diagrams for mirrors and lenses. So here is a list of lectures that you would like to watch. Each of them is about 10 minutes long. While you do that,
The lectures will ask you to do simple calculations to confirm the correctness of the ray diagrams that they show. To do that, you will have to use the mirror thin lens equation that I mentioned before. So in the second part of the video that you can watch either before the hippocampus lectures or after hippocampus lectures, I will briefly describe how to use the thin lens equation.